7th grade. So our learning target today is I can explore and use a variety of rates that describe common real-life situations. So here's our learning target today. So we're going to start with some definitions. We have, first of all, on the left, we have a ratio. A ratio is a comparison of two quantities using division. So you have two different groups of things being measured and being compared. You have 15 girls compared to 40 boys. You're still talking about all of that is related to the idea that we're comparing people into two separate groups. So we have two separate, we could say, groups of things that are being compared. That's called a ratio. Over here in the middle, we have something called a rate. A rate is when you have two quantities with different units. So for example, when you have miles being compared to minutes, so two different, totally different things. When you take a rate and you convert it to one of something, it becomes what's called a unit rate. So a rate with a denominator of 1, oops, I have a typo there, with a denominator of 1 is called a unit rate. Just a situation where we're taking the top number and we're dividing by the bottom number, and we get down to a unit rate. So the three terms working from left to right is that we have a ratio which compares two quantities or two groups. A rate is comparing two totally different things. And when we convert down to one of something, it becomes a unit rate. So what I'd like you to do now is I'd like you to list the following three. So you have three problems here using the terms rate, unit rate, and ratio, and put the proper name in each of those blanks. I'll give you some time to work. So again, you're answering questions 1, 2, and 3 with the three red words above: ratio, rate, and unit rate. Okay, great. Hopefully you've had some time to solve. So you should have said that this is a rate, because a rate compares two totally different things. We're comparing dollars and hours here in number 1. Number 2, we're comparing two different groups of things, or two groups of things, not necessarily different, but they're all people. We're going to break that into two different groups, so that becomes a ratio. And example 3 then, when we have a rate broken down to one of something, it becomes a unit rate through the operation of division. So go ahead and get your papers. Moving on now to number 4. Number 4, we have a subway car traveling 2.5 miles in 5 minutes. So we're comparing miles compared to minutes. That becomes a rate, two different quantities. So we would say is that we have miles being compared to minutes. We're asked to calculate the speed of the car measured in miles per minute. So 2.5 miles every 5 minutes. What is the speed of the car? So we really want to know how fast is the car traveling in 1 minute. So our job is really to take this as a division problem. Top number divided by bottom number, 2.5 divided by 5. So go ahead and type that in your calculator, unless you can do it in your head. 2.5 divided by 5 gives us 0.5 miles in 1 minute. That would be the speed of the subway car, 0.5 miles in 1 minute. So in part B then, we're going to use the information that we know of how fast the car is traveling. And we want to know if it travels 0.5 miles in 1 minute, how fast does it travel in 11 minutes? So we have many options on how to solve this problem. Many students would take a look at this situation. The speed of the car was 0.5 miles, or a half a mile in a minute. So some students would just say, well, I'm just going to multiply that by 11 minutes then, to find out that the car is traveling 5.5 miles in 11 minutes. That would be an option. Some kids would maybe set it up as two fractions. Any way that you can solve, but we need to come up with the answer that it's 5.5 miles in 11 minutes. Question number 5. We're really talking about speed here, which is really a rate, or your speed. How fast can you do something? So Nate can swim 200 yards in 3.5 minutes. So what we know about Nate is he can go yards compared to minutes, which becomes a rate. 200 yards in 3.5 minutes. If we want to know Nate's speed, We really want to know how fast is Nate going in 1 minute. So our job in this is to go from a rate to a unit rate. So we have a rate here on the left. We're going to break that down to a unit rate on the right. So we have the operation of division is happening there. 200 divided by 3.5. 200 yards divided by 3.5 gives us 57.1 yards. So we have 57.1 yards that Nate can travel in 1 minute. There's our speed, that's our rate or our unit rate for Nate. Just a division problem. Go ahead and check your work there and make sure that you're caught up. Okay, so moving on to number 6. In number 6, again, we're looking for the speed or the rate at which we can travel. What it says here is that you can bike 30 blocks in 20 minutes. So the things that I'm hearing are blocks compared to minutes. 30 blocks, 20 minutes. So how fast can you go in 1 minute would be really a measurement of your speed or your rate. So you have 30 blocks in 20 minutes. How fast can you go in 1 minute? It becomes a division problem. Top number divided by bottom number. 30 blocks divided by 20 minutes. You should be typing on your calculator right now, unless you can do it in your head. 30 divided by 20. You should be coming up with an answer of 4.5 blocks in 1 minute. So if you're traveling on your bike, you're covering 1.5 blocks a minute. We could probably assume that the blocks must be pretty long then if that's what it's taking us to travel. Depends on how fast you can bike and if there's hills and things like that. But that is the speed in which you're traveling. When we break it down from 30 blocks in 20 minutes is the same as 1.5 blocks in 1 minute. Moving on to number 7. In number 7, you can raise $48 walking 4 miles. So the labels that I'm hearing are, we have $48 in 4 miles. That's my rate at which I get paid. This is my rate. What we want to know is what is the unit rate, or how much per 1 mile for walking. How much for 1 would be our unit rate. Becomes a division problem, top number divided by bottom number. So we're really saying 48 divided by 4, typing that in your calculator, what is 48 divided by 4 to give us that unit rate? And 48 divided by 4, you should be coming up with $12 per 1 mile. So it sounds like it's like a fundraiser type situation, and you are raising $12 for every mile that you walk. That would be our rate of raising money. Number 8, the International Space Station travels 57.6 miles in 12 seconds while orbiting the Earth. Find the speed. Again, we're just looking for that unit rate when we're talking about speeds. The labels that we hear are miles compared to seconds. So we have 57.6 miles in 12 seconds is how many miles in 1 second? 57.6 miles in 12 seconds is how many in 1 second? It just becomes a division problem as we're trying to work it down to that speed. 57.6, typing in your calculator right now, 57.6 divided by 12. 57.6 divided by 12. You should have 4.8 miles in 1 second. 4.8 miles in 1 second. Checking your work there. 4.8 miles in 1 second. It's just a division problem, converting from 57.6 miles in 12 seconds. Division, break it down to a nice unit rate to kind of have an idea of how fast the travel is. Number 9. For number 9, we have that a case of pop. When you're thinking about a case of pop, you should be thinking 24 cans in a case. Costs $6.49. What is the cost per can? So we're asked about how much does it cost compared to how many cans. So we have $6.49. for 24 cans of pop? How much does it cost for one can? $6.49 for 24 is how much for one? This really becomes a division problem. 649 divided by 24. 649 divided by 24 gives us 27 cents for one can of pop. That is the cost per can. So this should be your answer. We're breaking it down. So that's a great thing to be looking at when you go to maybe a concession stand and you see that they charge you 50 cents a can or $1 a can. If you go to the grocery store, you're only paying 27 cents a can. But you go to a concession stand, they charge you $1 a can, or you go to a vending machine, they charge you $1 a can. You can see that the profit then, they're making a pretty good profit on that. That's why they stay in business in those concession stands and those vending machines, because they're making a profit of 73 cents per can, which is a good way to make some money. On the top of the next page then, meet me on page 2, question number 10. So again, we're going to still continue to talk about rates, but we're going to get into this idea of a rate really is a slope, or it's a speed at which something is happening. So we're going to start with number 10 on this page, this problem, to try to connect the two thought processes. So the graph shows the distance that sound travels through water. So we have a nice title here that says that we're talking about sound through water. And in question A, it's asking us, what does the point 2,3 represent? So I'm going to go ahead over here and identify the point 2,3. And I'm going to drag it down. As I drag it down, it says 2. 2 what? We're talking 2 seconds. So that 2 is really talking about seconds. Then I'm going to drag it over 3 what? We're talking about 3 kilometers. So we're really comparing 2 seconds with 3 kilometers. Moving on then. In part B, we're asked to find the speed, which is what we were just doing previously on the other screen, the speed at which something travels. So we're going to still use this data point of 2 seconds, 3 kilometers to represent speed. Now, when we're talking about speed, we really want it to always be represented using y over our x coordinate, y over x. So if I look at my y and I put it over my x in my table, my y value here is measured in kilometers. So y is kilometers. And my x value here, this is my x is measured in seconds. So we're talking kilometers per second. So as I start to look here, the kilometers, 3, the seconds, 2. Go ahead and organize it in your table. So we're going y over x. Kilometers was our y-axis. We go back and look here, it was the kilometers on the y-axis and the seconds on the x-axis. We want to know how fast, or the speed, which is just a rate or a unit rate. So we want to know how much in 1 second, like we did on the previous page. This really becomes a division problem. 3 divided by 2. 3 divided by 2, we have 1.5 kilometers in 1 second. So our speed at which we're traveling, the sound through water, is 1.5 kilometers in 1 second, which really is just our growth or our speed. So in question C then, it's asking how many kilometers will we be in 7 seconds. So I'm going to just take this information that I just solved, my speed. We figured out it was 1.5 kilometers in 1 second. So we want to know how much would that be in 7 seconds. So I'm just going to take that and multiply it by 7 seconds. 1.5 kilometers in 1 second multiplied by 7 seconds gives me 10.5 kilometers in 7 seconds. So the speed of sound through water would be traveling at 10.5 kilometers if it were traveling for 7 seconds. So this is just an option. Take your speed from part B, 1.5 kilometers in 1 second, and multiply it by 7 seconds. So really we need 7 of these. It gives us 10.5 kilometers in 7 seconds. Question number 11 then, we're going to compare of traveling through air as we travel through air. So going to our graph here, what does the point 4, 1.4 represent? So if I follow this point over and across, the 4 is representing the time or the seconds. If I follow this over, the 1.4 is representing the kilometers. So we're really comparing 4 seconds and 1.4 kilometers. We want to know the speed of sound in kilometers per second. So we have kilometers per second. We're really comparing our y to our x here. So again, here's our y-axis. The label on the y-axis is kilometers. Here's our x-axis. The label on the x-axis is seconds. So as we start to solve then, the kilometers is 1.4. The seconds is 4. So we have 1.4 kilometers in 4 seconds. We want to know how fast we're going in 1 second. How many kilometers in 1 second? Just like we did on the previous page, we're looking for the unit rates. So it becomes a division problem. 1.4 divided by 4. So everybody should be typing that in their calculator right now. 1.4 divided by 4. There's our division right there. As you're solving 1.4 divided by 4, you should end up with 0.35 kilometers in 1 second. This is the speed at which we're traveling through air. So as I move to question C then, in part C, how many kilometers would there be in 7 seconds then? So we have these kilometers compared to seconds. And according to my speed right here, I found out that it's 0.35 kilometers in 1 second. So how much would it be in 7 seconds? I can just multiply that like we did in the previous problem by 7. We're just taking that value, multiplying by 7, gives me 2.45 kilometers in 7 seconds. Go ahead and catch up if you haven't. So we're taking 0.35 multiplied by 7 seconds gives us 2.45 kilometers in 7 seconds. So now we're going to compare these two. So we talked about water versus air. So the top one was water, the bottom was air. If we look at the speed of sound in water, we decided that the speed of sound in water is 1.5 kilometers in seconds. This is the water. We go down and compare that to the air. The air's speed was 0.35 kilometers in 1 second. So it looks like that it's not moving as fast through the air as it does in the water. So does the sound travel faster in water or air? You should be saying that it travels faster in water. According to the answers, we're looking at the answers to numbers 10 and 11. And we're looking at numbers 10b and 11b and trying to see which of those speeds is faster. You should be saying that 10b's speed is faster. Okay, so now we're going to move into some real world examples of when we would find the unit rates. So for example, number 13, anytime you're buying something in a large quantity and you want to break it down to how much it costs for one of something, you would have that situation. In this particular case, the labels I have are dollars and compared to gallons. So we have $74.75 for 5 gallons. How much does that cost for 1 gallon? So go ahead and get that set up. So we have dollars compared to gallons. I have my dollars here compared to my gallons here. I know that's a little hard to read in that paint can. So how much for 1? Division problem, $74.75 divided by 5. Everybody should be typing that in. $74.75 divided by 5 gives me $14.95 for 1 gallon of paint. So your answer should be $14.95 for 1 gallon of paint. Moving on to number 14, and for number 14, we're going to take always y divided by x. So this table is going to end up switching a little bit or flipping, which happens a lot in math when you have to just analyze the data, but we really do need a y divided by x. So we're going to have our servings divided by our packages. Now in this table, really all I need to do is grab one of these data points, one of them. There are 4 available, 1, 2, 3, and 4. I just need one to compare the rates. So I'm just going to grab the first one out of the table. The y value in that first one is 3.5. The x value in that first one is 3. So we're saying it's 13.5 servings for 3 packages. So how many servings for 1 package? This really becomes a division problem. 13.5 divided by 3 gives us 4.5 servings for one package. 4.5 servings for one package. That's our rate. That's actually it's our unit rate. How much is it for one of something? Okay, 7th grade. We're moving on to number 15. For number 15, best unit rate question you can have when you're grocery shopping. So you have these dollars and these cans. Dollars on top, cans on the bottom. Go ahead and write. Everybody should be writing. Dollars on top, cans on the bottom. So our dollars, $4.80. We're going to go ahead and lock that into the numerator, $4.80. In the denominator, we say 6 cans, $4.80 for 6 cans. We want to know how much is that for one can. What's the cost per can? There's our unit rate. So we have $4.80 divided by 6 gives us 80 cents. Go ahead and divide that. $4.80 divided by 6 for one can. 80 cents for one can. That is our unit rate, 80 cents for one can. Number 16, same thing. We're still working for that unit rate. Why don't you go ahead and try to set up number 16 and solve. Okay, so hopefully you are at least able to try to get it set up with meters on the top and hours on the bottom. Hopefully you have a 54 here and you have a 2.5 there. And now we really want to break it down to how many meters in 1 hour. So I'm trying to go slow a little bit here to see if you can get caught up on that. There's a division happening there to get that unit rate, 54 divided by 2.5, 54 divided by 2.5. As you start to divide that, you should have 21.6 meters in 1 hour. 21.6 meters in 1 hour. Now I don't care about the rounding there, so maybe you have 21 point, I'm not sure if that was a repeating decimal. Let me go ahead and type it in, as I was just kind of doing those in my head. The 54 divided by 2.5 gives us 21.6, so it is not a repeating decimal. If we just round to the nearest tenths place, that's exactly what your calculator says there, 21.6 meters in an hour. That is the rate.